start. No. Go back. Okay. Just making sure the camera's looking at the right thing. So first of all, don't forget we have a tour of car tomorrow at 5?
I think so.
I think it's 5. And we'll meet over there in the lobby of car. It's probably wise to get there a few minutes early. Just checking the calendar, make sure it's really 5. Yes, 5. And he said it would take about 45 minutes, and we'll see electric vehicles and the hydrogen charging station and I don't know what all. And you know how Giorgio Rizzoni is. It'll be very exciting. The other announcement I want to make is that I have one more actual lecture for you, and then I'm going to do a review lecture. And there's one more lecture that has already been videotaped from a previous year on the smart grid. So all of this adds up to mean that on Monday of the last week of classes, that last day of classes before exam period, we won't have class. You'll be done by then. And you'll already have the exam. I'll post the exam. You have a homework due today, right? I think that's the last homework. So I think that I'll just post the exam and it'll be due whenever our exam would have been if we had an in-class exam, and I'll tell you in the email. So then you should be able to, if you want to finish this course a little bit early, you'll be able to. Is that cool? All right. So we were talking about heating, and we had mentioned that you can burn fossil fuel to directly produce heat, and that would be 78 to 90% efficient, depending on the oven and the fuel. And the question is, can we do any better and get off fossil fuels? So we're going to look at a couple of things. One is something called combined heat and power, and the other one is heat pumps. So recall that the power used is to heat something or cool it, is the average temperature difference times the leakiness of the building divided by the efficiency of the heating system. So temperature difference, climate is a factor we can't control, but you can control the thermostat. The leakiness of the building had to do with the thermal conduction and the air exchanges, the ventilation, how many times you exchange the air. And I believe you had a delightful homework problem involving doing that. Yes, you look all excited. So, air exchange, so it's good to insulate the building, but you still have to ventilate the house so you can breathe. And so you heated the house, but you have to ventilate it, so you're taking your heated air or your cooled air and you're cycling it out of the house so that you don't suffocate, and so that your toxins don't build up from the formaldehyde from your furniture or whatever. So since you've heated the air in your house, what would be nice is to collect the heat out of that air before you return the air to the outdoors. And so that's what we're going to talk about here. So modern furnaces will do this. So let's consider your nose. Let's say it's cold out. Your nose warms the air as it goes in. And air ends up at body temperature and it's hot when it's exhaled. So in your nose, the air direction alternates, breathe in, breathe out. But another approach would be to use 2 pipes, one for coming in, air coming in, and one for air going out, which is what furnaces do. And then what you can do is you have a heat exchanger. So you've got a vessel here, and there's a pipe with the cold air, or it could be a liquid, circulating through here, and so the liquids don't mix, or the gases don't mix, but they're exposed to each other and the temperature can change. So you can move the temperature from the hot to the cold and exchange some of the heat. So that improves the efficiency, and beautifully this uses no energy. It's just how the things are in thermal contact but not in actual contact. So here is an example. McKay has a friend whose house he calls Heat Keeper. It has a floor area of 100 square meters. The walls are 30 centimeters thick, about a foot. U value of 0.28 watts per square meter per degree C. So he's got 13 millimeters of plasterboard, 27 millimeters of airspace, a vapor barrier, 8 millimeters of plywood, 90 millimeters of rock wool, which I had to look up. That turns out to be a foreign language for the rigid kind of insulation. 12 millimeters of fireboard and 103 millimeters of brick. The ceiling is 100 to 200 millimeters of that rigid insulation with a U value of 0.27 watts per square meter per degree C. And then the floor's U value is 0.22. So you remember the numbers that we were looking at last time. These are excellent numbers. So heat keeper continue. The windows are double glazed, so they have a U value of 2. And they're oriented to pick up sunlight, so that contributes to about 30% of the home's heating. This house is very well sealed. Every door and every window has neoprene gaskets, so I'm thinking this guy is like compulsive. And then the ingoing and outgoing air passes primarily through the furnace via that heat exchanger we were just talking about. So if the outside temperature is -8, the air intake in the attic was about 0 degrees, and air coming out of the heat exchanger was +8. So we actually picked up 8 degrees right from the heat exchanger. So McKay, he didn't have that. He improved his house though in ways that we talked about before. So McKay, before he fixed his house, he had 21 watts per square meter was his average leakiness. McKay afterwards, he got it down to 7.1. Heat keepers 6.6, so they're comparable. The difference, McKay, remember, got the last little bit out of thermostat control. So he was wearing a woolly jumper in the winter, and the heat keeper gets there by a heat exchanger. It's not stated in the book, but he sort of implied that that's how he gets his last little bit. So let's look at some other buildings. So the National Energy Foundation building is in England, and it uses solar panels for hot water, so we know about solar thermal. It has photovoltaics producing about 6.5 kilowatts of electricity, which is maybe 30% of what the building actually needs. It's heated by a 14 kilowatt heat pump, and we're going to talk about heat pumps shortly, and occasionally by a wood stove in an office building. Isn't that so cute? 300 millimeters of insulation, again, that's about a foot. And its leakiness works out to 7.4 watts per square meter. So they worked hard on this building. I don't know what it is for the 4-H building. That's what we should have done. We should have had a tour of that building. Here's another building at the Cambridge University, the William Gates building. It incorporates many environmentally friendly features. And it won some award. And it's 25 watts per square meter. Wait, what was that last one? 7.4. So even this one's 25. Here's some more buildings here. The Gates building is about 30% more efficient than 1970s era technology. Let me find the Gates building. Here it is. 25. This is power per unit floor area, so based on the footprint. Here's the European average, about 33. Here's McKay's house before he fixed it up. Here's his house afterward. So even before he started working on it, it was below average. Heat keeper was 6.6. This is offices, UK service sector. This is a 30 watts here. DIFD, I don't know what that is, 43. This inset says 170 kilowatt hours per year per square meter, University Arts benchmark. But these are different units. This is per year. Home office, this is 45 watts per square meter. NEF office, 7.4, we just looked at. Elizabeth Fry building, UEA, United, I don't know what that is. Do you know what that is? UEA? Me either. 11. Cambridge University, so typical building there, 37. Old schools, whatever that is. Old schools predate 1900. 34. Rutherford building. Here's the Rutherford building. I guess it's on Cambridge campus. 36, law facility, law faculty, excuse me. Very fancy looking. This is not our law building, even though ours is pointed like that. 22, and the Gates building there is 25. So just to give us some ideas of different kinds of buildings. Lowest one on here is still the heat keeper. So let's compare McKay's house after he fixed it up, 7.1. The NEF office at Super National Energy Facility, whatever it was, 7.4. Gates building 25. European average house 33. This is in watts per square meter of building footprint. Okay. On this side, we're comparing now how much energy could you get per square meter of footprint from these various fuels. Biomass less than a half. So if you were using all biomass, you wouldn't come close to heating these homes. Wind, 2 watts. If you, instead of having biomass, you had wind, actually you could have wind and biomass on the same square meter. We could add those up, 2.5. Still not enough. All right, we reject the biomass, we put it in solar panels, PV, 20, that'll cover some of these. Or solar thermal, but again, this is thermal heat. Of course, if all you're doing is heating the building, maybe that's okay. So basically, you have to work hard to make a building self-sustainable energy-wise. But it can be done from these numbers. So let's look at combined heat and power. And I think we talked about cogeneration before. So the idea is you have a power station. The power station generates electricity by burning something. So you burn the fuel, the heat creates the steam, for example, and the steam drives a turbine, and then you have to dump the heat. So the steam goes through the turbine, turns it, and it's still hot when it comes out, so you have to dump it into a cold place to generate the energy. So why not make the cold place a building that you wish you could heat anyways? The catch is you have to have your electricity production near the thing you need to heat. Like you have to have the coal plant in your backyard if you want to heat your house. But this is called combined heat and power, or cogeneration. Why not? Sounds pretty good, except for there's no free lunch. So if you burn fuel to generate heat as opposed to generate electricity, it's more efficient. But heat's not as good a form of energy as electricity, so it's more efficient for generating heat. Even though CHP captures waste heat, it does impair the power station's ability to generate electricity, conservation of energy. So you have some waste heat, but it's putting kind of a drain on the generation. The gains are smaller than people make out, according to McKay. And the other issue is you can't transport heat easily. So again, you need to do this near the thing that you want to heat. So let's talk about heat pumps then. So the idea, here is the air source heat pumper. The idea is that you have heat from the outside, and you want to pump heat in, so you have electricity, a heat pump here that runs by electricity. You have a heat exchanger here, or in a ground source heat pump, and you could be pumping heat either direction, depending on if you're heating or cooling. So here is heat from air warms the top layer of the soil. You got a ground collector here, again a heat pump. So let's take a look at those. Basically, you can think of it as a backwards refrigerator. So fridge moves heat from inside the box out into your kitchen, which is why it's dumb to open the door, the refrigerator, to cool off. They have cartoons of people doing that. So why not let the inside of your fridge actually be the backyard? So you can move heat from the backyard into the house, just like you did from the box. Actually, it's fairly efficient. For every kilowatt the fridge uses, it can actually move 3 kilowatts of heat. It's not creating that heat. That's why it sounds like you're getting something for nothing, but it's not. It's moving heat from one side of the wall to the other. Plus the 1 kilowatt that the fridge uses, that gets converted to heat. So the total efficiency is actually 400%. That's counterintuitive because everyone knows there's no such thing as efficiency above 100%. So again, because I struggled with this also. The reason is it's burning the 1 kilowatt, but it's using that energy to move heat that already exists on one side of the wall to the other side of the wall. So the coefficient of performance, we say, is 4. So let's examine the idealized, and let's note that it's idealized. If you want to move the heat from the cool outside, so it's cold outside, you're trying to heat the inside, you want to move it to the inside, the efficiency is T2 over the difference in temperature. If you want to move the heat the other way, it's T2 over the other difference in temperature. So if you want the efficiency to be high, you want this denominator to be small, which means you want these two temperatures to be close to each other, which means that the more heating you need, the less efficient it is, or the more cooling you need, the less efficient it is. So the closer these two things are, the more efficient. There's no surprise there. But you can still do it, and you can pump heat in other directions. So this one shows a hot area going into a cold area, so you can move heat, take heat from here and move it to there. Or you could go the other way around. Does it really pump heat? No. It works like an air conditioner. So heat from one side heats a compressible fluid, like a refrigerant, and you compress that, so there's mechanical work. You need electricity to do that. You run it through a heat exchanger or a condenser, and condense back to the high pressure fluid, which is at a moderate temperature. You pump that to the side that needs to be cooled, and when the fluid expands, it cools even more, absorbing heat from the surroundings. And the fluid boils, it goes back to a gas, and you repeat this, which is just exactly how an air conditioner works. But it's air conditioners moving heat from inside your house to outside. Air source or ground source. The ground temperature is usually pretty close to building temperatures. Once you get below the 3 feet or so, the ground temperature is uniformly 50-something degrees, at least around here. So your house isn't going to be that different. But it's hard to drill those wells for the pipes, as anyone who lives on campus knows. And especially if your house was already built, so this means you have to tear up your south oval for years. People are not happy about that. And was it one of you guys that said something at the Yelgin's, what's that guy's name? Jurgen. Yeah, was it you that said something?
No, I was there from.
Yeah, but somebody he was pretty bent about it. Well, anyway, so if your yard is already nice and grassy, you don't want to tear it up to build those things. And the other thing is, if you have too many people doing that and they're all trying to suck heat out of the ground, they can suck so much that the ground changes temperature and it gets less efficient. Or if you're dumping heat into the ground, same thing. If there's a lot of people doing it, you can actually heat the ground up locally and reduce the effectiveness. So let's say you decide to let the sun warm up a big giant rock and you put that rock under your house. Then on a cold day, you could recover that heat to warm your house. So we want to know, how good is the rock at storing heat? It isn't really a rock, of course, it's the rock underneath your ground, underneath your house. So let's say you're going to use this rock idea and you want to heat the rock to 50 degrees C. And to heat your house for a month, you require, say, 24 kilowatt hours per day. Now the heat capacity granted is 820 joules per kilogram. And the mass that you would need is the energy that you need, kilowatt hours per day, over the heat capacity times the temperature difference. So we have 24, what's the 30? 30 days, 3.6 megajoules. Where's that coming from? It must be a conversion factor. Here's the heat capacity of the rock. Here's the temperature difference. He's saying that the ground the rock is 50 degrees C, and he wants to get to 16 degrees C? That doesn't make any sense. What's 16? That must be a woolly jumper temperature. It ends up being 100,000 kilograms of rock, so that's a meter thick by, I forget what the dimensions are, but almost the side of your house. It's a big chunk of rock. Okay? Now, if you need to insulate that, if you don't insulate the granite slab, then it increases from 6 meters square by 1 meter thick to 20 meters by 20 meters by 20 meters. So you would, if you're going to use the rock, you have to put insulation around there, keep the heat from leaking into the surrounding ground. The heat pump, we should be clear, is different than geothermal. And what they're doing on South Campus is actually geothermal. So geothermal harvests heat that's trickling through the crust from the mantle. Now wait a minute. In the heat pump, you're heating the rock and extracting heat, or you're extracting heat from the dorm and putting it into the rock. And the reason I'm saying wait a minute is they're calling them geothermal wells, but didn't they say they're going to provide some air conditioning? So I'm thinking, and over at the 4-H building on West Campus, they call that geothermal, but they actually get air conditioning from it too, and they're pumping fluids and exchanging heat. So I think that's really a heat pump. A geothermal, McKay makes this distinction, harvests heat trickling through the crust on the mantle. So you can only bring heat up, and you're sucking heat out of the earth instead of letting the sun heat the earth. Ground source heat pump, the ground is reasonably insulating, it's good, the rock doesn't cool down too fast, but when something's reasonably insulating, it's hard to move heat through it because it's insulating. So, let's consider crowded neighborhoods like maybe a dorm. If we all suck heat at the same time, we would freeze the ground solid. True? False? False. We have one vote for false. Maybe. We have people who refuse to commit because they know I'm going to tell the answer anyways. Well, calculation. Oh, wait, we're not supposed to use calculus in this class. So, mumble, 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 mumble. Oh, look, here's the answer. Results. For a suburb with a population density of about 160 square meters per person, the limit of heat delivery is something like 19 kilowatt hours per day per person. So that's probably not enough for my heat and hot water. So probably not everyone can do this at the same time. So even on the South Oval, when they're doing that, it's going to provide some of the heating and cooling for those buildings, not all of it. And there aren't dorms on all four sides of the South Oval. Another calculation. So how much power could we suck from a ground loop 2 meters deep? So this is asking about the rate of heat transfer, not the heat stored. And we go mumble, mumble, mumble. We put some frightening equations up with integral sign just to make ourselves look important. Oh, look, here's the answer. 12 kilowatt hours per day per person. That should say kilowatt hours per day per person. From a ground loop 2 meters deep, which I believe is what they have out at the 4-H building. So conclusion, if everyone in your neighborhood were to suck heat from the ground in the winter, you'd have to make darn sure to replenish that heat in the summer, which in our climate, perhaps we could do. Okay, let's compare combined heat and power to heat pumps. Combined heat and power, again, is you are generating power anyways. There's some waste heat. You try to reclaim some of that heat. A heat pump, we just talked about, is an air conditioner or a refrigerator working frontwards or backwards. Now in the UK, they use mostly boilers. So we say furnace, they say boiler, because there's really are boilers. They boil water to create steam, and then they circulate steam through these old radiators. And my house growing up had that. Some houses do, but in the US, we mostly use forced hot air, which has a grate like that, and we call them furnaces. So when he talks about radiators, that's what he's talking about. So condensing versus a standard boiler. In a conventional boiler, you burn fuel, you heat the gas, and then you have a heat exchanger, which heats the water. So you got the gas, you got a pipe full of water going through this hot gas, and the heat transfers to the water. You circulate the water through the radiators, and then you transfer the heat from the water here to the metal. You can imagine that, and it radiates out to the air, and then what's coming out is pretty cold and returns to the basement, gets heated again by burning fuel. A condensing boiler, you burn the fuel, the combustion produces hot gases, which contains water vapor. So you still have the hot gases, but now you condense the vapor to extract the heat. Okay? And you pick up another little bit, another 10%. Now he claims you can get up to 98% efficiency using a condensing boiler, and I just put a condensing furnace in my house recently, and I think its efficiency is more like 90%. But still, it's better, reclaiming some of that heat. So for us, we use forced hot air, so our circulating fluid is actually air. We burn fuel, we heat the air, or in a hydronic system, I never heard that word, it's water. Again, you use a heat exchanger to keep the combustion byproducts out of the air that goes into the house. You can't really tell here. You got heat here, and it's heating this, it's inside this envelope of air, and the air gets heated, and notice that these gases, which have all the particulates and poison for the fire, that goes out somewhere, but you've got the heat, and it just gets pumped around your house. So the hot air is blown via fan, through ducts to the rooms, and then the cold air, you have cold air returns, and cold air naturally goes down, returns to the basement. Here's a fan that pumps it through here and heats it up again. All right, so here is a plot of heat efficiency in percent, and it goes from 0 to 100, and electrical efficiency in percent, and this goes just plots from 0 to 60. This line here, new standard solution, this standard, old standard solution. So here, down here, he's got a coal burning. If you're not trying to get any heat, you're just trying to get electricity, you burn coal, you're down on this line, you've got efficiency of 30-something% in this case. If you use a standard boiler and you are not trying to burn electricity, you're just trying to make heat, you can get up to 80%. If you're trying to combine heat and power, you'd be somewhere on this line. Now the new standard solution, here's gas, and this is B, I don't know what that stands for. Here's a best case, we won't look at that. 50%, if you're just trying to make electricity, condensing boiler up here is better. You can get maybe 90% efficiency if all you want is heat and you don't want electricity. If you want both heat and electricity, you're somewhere on this line. The point is that you give something up, right? There's a trade-off. So the cogeneration is helpful, but it's not perfect. This way, on the plot would be better, more efficient electricity, more efficient heat, and this way would be worse, but of course these lines are orthogonal to that. 90% efficiency means that 10% of the energy goes up the flue as heat. And efficiency to create electricity in a power station, UK is apparently moving away from coal to gas, or at least was at the time that McKay wrote the book. I think that's why he calls that the new, better solution. Now, let's say you have a bucket of gas, and I guess it's natural gas, and you decide, well, I have this gas, I'm going to burn it. How much do I want it to create electricity, and how much of it do I want to use to create heat? So you move up and down this line and decide how you're going to use that. So you know, how much for heat, how much for electricity generation. There's no free lunch. So why not use all of it to make electricity and then use the electricity to create heat? Yeah, conversion efficiencies, right? We've been saying this all semester long. Last thing you want to do is use electricity to make heat, because you make heat to make the electricity in the first place, so there's conversion losses. And I have no idea what, evidently the animations are screwed up. Converting fuel to heat, more efficient than converting fuel to heat to mechanical to electrical energy, which is what you just said. And then producing heat. And also remember that heat is low quality energy, so you can use it for heating, but that's about it. Now, here are some real CHP systems, combined heat and power. The filled dots are actual systems, so he's quoted some here, some specific ones, and he has citations for them. Hollow dots, CT are ideal systems. CT. What's CT? I don't remember. Nimbus are manufacturer specs, so there's some dots named Nimbus over here. The point is that combining heat and power reduces efficiency for both. Here is a gas turbine reciprocating engine, right around, I guess it must be this pink one. Pass out condensing steam turbine here, back pressure steam turbine, standard boiler, condensing boiler, and these are some fantasies. Notice only the filled dots are actual systems. So if someone's been able to get this, I wish I could remember what CT stands for. It might be a brand. I only say that because these other ones are brands. So is the net efficiency better? Some dots are closer to the better corner over here than on this line. Drawbacks that CHP delivers heat only locally. Back to this business of if the power generation station is in Muskingum County and I want the heat, I gotta move to Muskingum. That'll make a long commute. Condensing boilers can be put anywhere where there's a gas main, and this is why I think when he says gas, he means natural gas. And you can decentralize heating if you can do that. CHP is not too flexible. There's an optimum mix. You can produce excess heat when you have a spike in the electricity demand, such as when the AC comes on. Well, wait, what was that about decentralized heat? You notice that right now that we have no heat and no air conditioning in the building? That's because we're switching over to air conditioning. And the way the university does this is OSU's heating and cooling is provided by the McCracken power plant right back there. You've probably seen it. There's giant chillers here. Now this is a picture when they were on the side, now they're up on the roof. And what this building does is it has boilers in it, and it generates superheated steam at 660 degrees Fahrenheit. That's very hot. The boilers are multi-purpose, so technically they can burn oil, natural gas, or pulverized coal. And they actually used to have a train track that came from across the river near the train tracks, the real train tracks that go up in north and south. And they had a spur that came over to campus, and coal would come over to McCracken. And on football days, people could take a train from the main tracks over to the stadium. I digress. Used to use coal, but they removed the scrubbers in 2005, so we're not using coal anymore, and I have no idea what we're burning right now. But they burn something, they generate heat, superheated steam, and the steam is piped to buildings via underground network. So in front of Dries right now, the sidewalk's all torn up. Those are the steam tunnels. That's where those pipes with the steam go. Superheated steam goes over to the business school and down to who knows where, and they also have pipes going east from here. So steam is piped to buildings via an underground network, and you can see the tunnels through the grates in the sidewalk on Neal Avenue, except for right now there's fences there so you can't see it. And then in the building, like this building, there's a heat exchanger that will take the heat from that superheated water and move the heat from the steam to pipes in the building. Now the steam isn't transferred, remember, the steam goes around the pipes of water, and the water circulates to the building that heats the room. McCracken also provides chilling or cold water year-round. 2,000-ton turbine-driven centrifugal chillers, 5 2,000-ton dual compressor electric centrifugal chillers, 2 775-ton electrical centrifugal chillers, a 450-ton electric rotary screw chiller, 19 cooling towers, and a plate and frame heat exchanger had been installed to supply some of the campus from a central chilled water system. This information I got in 2010, and Scott Potter was here to tell us about the new chiller building for the hospital. Kind of interesting to know how these things work. So air conditioning year-round, why would we want that? Well, it turns out we have some specialized labs in this building. If you want to go down to the basement, wander around, there's a lab in that corner that has the clean room. So the clean room, these are diffusion furnaces, it's ultra clean, and they need AC all the time. And in fact, this is the molecular beam epitaxy machine, and it has to run under vacuum, and the vacuum is created cryogenically. And you know that big white tank they just put outside? That is full of liquid nitrogen. It supplies the clean room to provide the cryo chilling for the molecular beam epitaxy machine. That tank, there used to be one in the parking garage. It was a little bit smaller, but not much. And they had to fill it 3 times a week. That's how much liquid nitrogen we use. With the new tank, I think they're only filling it like once a week because it's bigger and it doesn't leak. And the old one, it leaked, and the company came in and they said, you know what? We're pulling this tank out of here because they were afraid that something would fail and the nitrogen would come out and flood the parking garage. Of course, no one would be able to tell. And their worst nightmare was people would be tailgating in the parking garage and they'd all suffocate to death because of the nitrogen leaking from the tank. So when they built this part of the building, the clean room guys, my colleagues, said, we want this big nitrogen tank to be where the new one is now. And the architects said, oh no, we can't have that, it's too ugly. And they insisted to be put in the garage. So they wasted all this money because they ended up having to move it out here. Anyhow, but we're not bitter. Alright, so CHP using combined heat power using heat pumps. So you use electricity from the grid. You pump heat into the buildings from some stored heat mass like rocks underneath the building. It's better than conventional cogeneration, even if electricity is created at a remote site by burning fuel. So here is, this part is the plot we were looking at before. Here's a heat pump with a coefficient of performance of 3. And here's where some of these guys are. And here's a heat pump with coefficient of performance of 4. Here is 30% efficient electricity, 80% efficient heat. So you get some improvement there. Heat pumps. If you're heating buildings with natural gas, you could install condensing boilers, which are 90% efficient, or you could use gas at some power station in Muskingum County to generate electricity, then use electric heat pumps in the buildings to suck heat out of the ground and put heat back into the ground. In efficiency would be between 140 and 185%, accounting for the converter and transmission losses. So if you're going to do that, you don't have to generate your electricity locally. If you're going to do this, you can generate the electricity down in Muskingum County. I always say Muskingum County because there's a coal plant I ride by on my motorcycle every summer. It's very beautiful, and they're going to change it from coal to natural gas because natural gas is cheaper now. You don't have to dig holes. Could you use an air source heat pump? So the idea here is that it's cold or hot outside. So here we have a wall. This is the outside, it looks like, and heat is discharged. This looks like an air conditioner. Coil removes heat from the air. Cold air blows back into the house. This air heats this. It goes into this condensing boiler, which condenses, chills the air, comes back, or chills this fluid, comes back in, and heat is discharged outside. So that's looks like an air conditioner. In winter, though, the heat pump draws the heat from outside, so the direction is reversed. And you get heat, so it's cold out, and you're making it even colder. Just like in summer, it's hot out, you make it even hotter. And you can suck or make the heat go into the house. But remember, if they work best when the temperature difference is small. My parents in Vermont actually have a heat pump, but it doesn't help a lot. And their temperatures tend to be pretty extreme, especially in winter. So, to summarize, we have 3 different things that affect the energy required for heating homes. One is the temperature demand, over which we have some control. One is the leakiness of the house, which takes money to fix that. And then how do you produce the heat? And all of them can be improved. And finally, heat pumps have better than 100% efficiency. So that's pretty cool. Where we are now, we've figured out that we can improve transport. We can improve personal transport a lot. We maybe can improve cargo transport a little. We can improve heating some. There are some renewable resources, but they're expensive and not widely deployed yet. What should we consider to be a sustainable answer? Question is, can we live sustainably on fossil fuels? So let's take a look at that because we don't have wind and solar in great amounts yet. So let's take a poll. Which of the following is based only on renewable sources? Oil for cars. Uranium for nuclear reactors. Coal. Lithium. None of the above. Right, none of the above. Finite resources. So there's only a finite amount of all of those things. Oil and coal turn out the best use for those is really making plastics. Currently, 5% of the petroleum in the U.S. is used to make plastics, which is amazing because you think of how much stuff is plastic. Wow, we must be burning a lot of gasoline. A car uses 5 to 10 times its weight in fuel over its lifetime. Wow. I would have thought it was more. 1 kilogram of oil equals how many kilograms of plastic? I just tried to find it out. I wasn't able to find it out. Uranium is limited but underexplored. It has few uses other than nuclear fuel. Dye and dense armor-piercing warhead. We talked about that. Lithium is used in batteries but can also be used as a nuclear fuel. So sustainable concepts, the reserve to production ratio. So you have 2 ways so there's reserves out there and we're going to be producing electricity or whatever energy from those resources. How long can we sustain that? So there's 2 ways to look at it. One is, how many people do we have? Let's divide by the amount of stuff we have and we can figure out how many years it'll last. That's what many people do in the press because it's easy. But actually the population is growing. And the energy demand is growing even for the population that we have. So if you look at growth limited, then you're going to get a different number. And what is sustainable production? So the reserve to production ratio looks like this. If R is your current reserve supply of oil, let's say oil, and P is the rate of production, so use of oil, and T is R over P is the supply duration. If you have 100 billion barrels and you use 1 billion barrels per year, it'll last 100 years. Ipso fatso. So that would be the simple model. So the simple model here says that we produce this much, we produce at a constant rate, and at this amount of time we run out of reserves. That's the equation we just had. But if you believe that our use is going to grow over time, and I believe this, Then you have this ugly equation here, and it says you're going to continue to use more and more oil at a faster and faster rate, and you're going to run out sometime sooner. Energy use has steadily grown, as you know, and not only that, the population is growing, and places like China are increasing their rate of energy use. So simple reserve to production ratio only works if we assume that society stops growing. Draw your own conclusions. If the growth rate is alpha, then math. If the whatever this is much less than 1, then the constant model is good, but we don't think it's going to be good. Very small. And here's engineering speak. That requires the growth rate to be very small compared to the reserves over the population or the production. So here's some examples. We got coal. Let's say the reserve is 1,600 gigatons, and we're currently producing 6.3 gigatons per year. We can take the ratio for the constant or the growth limited. And for oil, we got a couple other numbers here. Let's see what happens when we fill in the table. The oil reserve, by the way, includes tar sands. Liquid petroleum reserves are only 1/3 this number. If you use the steady model, we have enough coal to last perhaps another 250 years. If you use the steady model, we might have enough oil for 120 years. But if you take into account the growing population, and these numbers will vary depending on how fast you think the population is growing and how fast you think people in other countries are going to start, and us too actually, increasing our rate of use, maybe we're looking at 70 years and 50 years. And the question is, do we want to call that sustainable? Will we come up with something else in that amount of time? So how many years supply do you want to call sustainable? Let's take a poll. This is a matter of opinion, by the way, so you can't get this one wrong. So maybe you're satisfied if we have enough stuff to last 100 years, and in 100 years we'll have found solutions. Maybe a lifetime. How about 200 years, your lifetime and your kid's lifetime? Maybe your kids are going to grow up to be engineers and going to fix all this. Maybe 500 years is how long we think the country will last. You go for that? That seems like a reasonable number. How many people say 1,000 years, a lifetime of a culture? Okay, we have more people who go for that. How many people think we shouldn't accept any of these numbers? Okay, we have a couple votes for that. None are wrong. What is sustainable? It has to be slow. It has to allow plenty of time to find alternatives. For what we're going to do, we'll just pick 1,000 years, but again, you know, your numbers may vary. We'll just use this so we'll have something to put in our slides. So perspective, so 1,000 years perspective. The oldest continually settled settlement in the world is 5,000 years old. That would be Byblos in Lebanon. And 1,000 years ago, what were our key resources? Wood for shipbuilding and burning. And important resources changed with culture, so they weren't burning much oil back then. We've talked about coal before. Worldwide reserves are about 1,600 gigatons. 1 ton gives you 8,000 kilowatt hours of energy. It's chemical energy, not electric energy. That's 6 kilowatt hours per day per person for all the people in the world for 1,000 years. All the people currently in the world for 1,000 years. 6 kilowatt hours per day per person. What's the average person in England using according to McKay? 195. All right, standard coal power station efficiency is 40% efficient. So if you're going to convert the chemical energy to electrical energy, we're looking at 2.2 kilowatt hours per day per person for 1,000 years based on coal. But of course, we don't like greenhouse gases, so we really should use clean coal. So if we use clean coal, that knocks the efficiency down some more, 25%. If we want to use coal for 1,000 years, we can use it at a rate of 1.6 kilowatt hours electric per day per person, and assuming we don't increase our rate of consumption. So clearly, and we already knew this going into this course, coal is not going to be sustainable if you're looking at anything like 1,000 years. In fact, that earlier chart said 70 years. Sustainable use in kilowatt hours per day per person. Coal, current rate of use, 23, and these are from his chart, so there's some citations there. Sustainable, 6 years. Oil, 24.3. Numbers in parentheses. Oh, I'm sorry. That's not a reference. That's a result after clean conversion to energy, to electricity. So a barrel of oil is about 1,700 kilowatt hours, and a ton of coal is about 8,000 kilowatt hours. So if you total the coal and oil, you get 47 kilowatt hours per day per person for current steady model. Why doesn't this add up to anything close to the 270 kilowatt hours per day per person we're already using in the U.S.? Because it's divided over the whole world, and we're using energy at a much larger rate. So we took how much oil and coal are left in the entire world and got this, but we're using this. So that works out to a sustainable rate of production of 1.6 gigatons per year. What is the current rate? 6.3 gigatons per year and rising. All right, suppose we just use the coal in the U.S. We have maybe 275 gigatons and 300 megapeople. So that works out to 900 tons per year or per person, or 82 kilowatt hours per day per person for 1,000 years. That's at our current population and rate. U.S. Energy Information Administration predicts 1.1% increase in usage. Coal reserves will last another 119 years. Estimate includes undiscovered resources, right? We saw that before. They might be there, you never know. And it does include going to carbon capture sequestration. This says recoverable reserves at active mines. That's this tip right here. This is estimated recoverable reserves of coal as of January 2010. So with this recoverable, estimated recoverable, this is demonstrated reserve base. This is identified resources, and I can't read that. Something in reserves, I can't read it, but this last one is total reserve, observed and undiscovered. Better hope we're right. Is 1.1% a realistic rate of increase? McKay says 2% fits the data for the last 70 years, and he doesn't say whether that's for England or worldwide. So the global reserve of coal is enough for 60 years if you use a 2% figure. So conclusion, we're better off than most countries. It's great to be rich. We still can't sustain our lifestyle on coal for any realistic length of time. Coal, even with carbon capture and sequestration, is a stopgap measure at best. Sustainable use will be much smaller than current use if we're going to just rely on coal, or even just coal and oil. So we got to fill in with something. And we need to support our growth from somewhere else. And that's going to be the topic of our next lecture. Current use, reserve to production ratio we talked about. Growth shortens time to depletion. Fossil fuels are going to run out in a few generations, maybe sooner. There you go. Sustainable use, if you call it 1,000 years, then we need other sources of energy, period. All right, we are done. I will remind you, for those who came in late, car tour tomorrow at 5 at the Center for Automotive Research on Kinnear Road. Be there or be square. Georgia Rizzoni is personally going to lead it, is my understanding. And I also mentioned that we'll have lectures. We have 2 lectures next week, and the following week, the last day of classes, we won't have a lecture because I'm going to ask you to watch a video of a thing about the smart grid, and it's fairly long. So I might cut our last lecture, in-person lecture, short. But anyways, we'll meet on Monday and Wednesday of next week, and meanwhile, I'm going to put up the exam shortly, the final exam, take home just like the midterm, and it's going to be like the homeworks, just like the midterm. And you have until whatever day our exam would have been if we had an in-class exam. That's when the exam's due. And I'll send that all out by email. I'm just giving you a heads up. Okay? All right. Run and play. Huh? Oh no.
Record.
Don't tell me. Oh, phew.